So everybody, I want to make up a whole new variable. Call it x. And x represents the number of people in this room. Could x be equal to 3.2? No. I mean, x can only hold values of 0, 1, 2, 3, 4, 5 up, and on up. And since x does not represent a variable that represents a continuous flow of real numbers, I might subclassify the variable x as a discrete variable, because it only holds integer values. In that particular instance, non-negative integer values. So a discrete variable is very different from a continuous variable. A continuous variable might be the variable y, representing the height of an arbitrary person's room. I think that would be a non-discrete variable, a continuous variable, because my values for y can range over an entire collection of real numbers, not just discrete numbers. Do you guys see the difference? You've been spending your entire mathematical career, or shall I say, most of it, dealing with continuous variables. A lot of what we're going to do now in this next chapter is dealing with a discrete variable, because I'm only going to look at nice, clean, natural number values for an input variable that I might refer to as n. Specifically, what I want to talk about today, among other things, is what we call a sequence. So let me start our discussion on sequences. So how about a formal definition? I've got two of them. I don't know which one you're going to like better. Here's one definition. Think of a sequence as merely a list of numbers. Here's a second definition, and I'll clarify this with my examples. Second way you can interpret a sequence is that it's a function whose input, whose domain, is restricted on some subset of the integers, not a continuous variable. Let me give you an example.
Say that again.
Yes. My second definition of a sequence is the following. You can think of a sequence as a function whose domain is not the reals, but whose domain is some subset of the integers. Let me give you my very first simple example of a sequence. Now, when I put that last comma and then 4 dots, it's clumsy notation suggesting to you, the reader, that whatever pattern isn't here, then it's going to repeat itself indefinitely. I think that's a list. I think that's a sequence. Matter of fact, I might even change my notation a little bit. Maybe I can think of the first entry as an A and the second entry as an A. And the third entry is an A. Same with the fourth. Oh, I can't do this, can I? Shoot. This isn't going to work. Darn it. They all look the same. So, if you don't mind, I'll use subscripts. So you can see that there are different terms in my sequence. I think I can write it a little bit differently. I can think of the first entry as a function f evaluated 1. The second entry is my function f evaluated 2. The third term is my function f evaluated 3. Can you guys really see that I'm accurate with my English? I really can think of this sequence as a list of numbers that a result is taking some kind of function f that's only evaluated on a subset of the integers, in this particular example, namely the set of natural numbers. By the way, what is the pattern involved here? I'm adding to each entry to get the next. And so if I asked you guys to consider the nth term of my particular sequence, do you think you can explicitly give me a formula? What would it be?
Plus 2.
5 times.
5 times 1.
Plus 2 times n.
It's close, it's close. Anybody else?
3 plus 2.
Ooh, that was nicer. Is that working? It's not working, but he's so close. He's right there. I think for the first term, how many times do you want to add 2? 0 times.
0.
For the second one, how many times do you want to add 2?
Once.
1. For the third term, how many 2's do you want to add?
2.
1 less.
Yep.
Then for the 5, why don't we just add 1 less than n 2's each and every time? Check me, see if I made a mistake. If n is equal to 1, I'm adding nothing to 5. But if n is equal to 2, I'm adding 2 once to 5, etc., etc.
Wouldn't that be the same as 3n plus, or I'm sorry, 3 plus 2n?
Yeah, I agree. You can get rid of parentheses if you want, clean it up. Looks like a nice, clean, linear expression. It corresponds to a line in the xy coordinate plane. I agree. I just didn't bother. I was just writing it naturally. You guys notice something. This is the means by which I can list an arbitrary term in my sequence no matter how far out I am. I sometimes refer to that as an explicit formula. Describing my sequence because you just plant your feet at where you want to be, and this nifty little formula will tell you what the term is in that particular sequence. Sometimes I like to give something a little bit different, though. Sometimes I like to give an implicit or recursive formula or description of my particular sequence. And I think giving a recursive or implicit formula is quite a bit different. It sort of amounts to this. Jump up in the air, plant your feet at any term in this particular sequence, and tell me how to get it from its predecessor. So, how do you get a 15 from a 13? Or how do you get an 11 from a 9? Or how do you get a 7 from a 5?
So the
Previous term at 2.
You take your previous term and add 2. So I think my a sub n is going to be equal to its predecessor no matter what it is, increased by 2. Let's see if I made a mistake, guys. Can we check this out? If a sub n is 4, I misspoke something. If a sub n minus 1 is 4, what's the next term? If this whole thing is 4, what's a sub n? 6. And so do you see a 4 followed by 6?
no.
Oh, shoot. What went wrong? What went wrong?
You started before the sequence.
I think I need to come back to where this particular sequence started. With a recursive or implicit formula, it's not good enough just to say how you generate one term from its predecessor. You also have to state how the heck you're going to start this entire sequence off. And so I think I need to proclaim that a sub 1 is equal to whatever the heck it is. Now with this recursive formula here, I can easily see what a sub 2 is because I know what a sub 1 is, etc., etc., etc. Did you guys see my point? All right, let me hit you up with some notation. Notationally speaking, I have not said or written anything incorrectly. But I don't think I've even once right now given you some closed notation for the sequence. So here's the notation. My sequence is I talk about my a sub n. I use braces around it. And sometimes I say to the reader that n starts at this particular value, but goes off indefinitely. This is an infinite sequence. Now I've got to confess, sometimes I get a little lazy, and sometimes if it's understood for you, the reader, that n starts at 1 and just increases without bound, I might sometimes just say, oh, consider this sequence right here and suppress that notation. Sometimes I might come in here in either one of these two cases and explicitly tell you what a sub n is. Whoops, hold it. Which in this case I forget. Is 5 plus 2 times? N minus 1. But again, at this stage of the game, you guys, a sequence is nothing more fancy than just simply a list of numbers or functions output is determined by a restrictness domain to some subset of integers. How about this example? You guys recognize it?
Fibonacci.
Yeah, I might refer to this as my Fibonacci. And the way I generate the Fibonacci sequence is I talk about the first entry, which is a 1, the second entry, which is a 1, and now from here on out, subsequent entries will be determined by summing together the 2 previous terms. And so if I were to describe this particular sequence recursively, I might say that any term in my sequence is nothing more than the sum of its 2 predecessors. Oh, shoot. If you guys look at my recursive description though, there's something a little bit different about this one. Notice how it is determined in terms of two predecessors, not just one like in my last example. So I think in this particular case, I better give you the very first two terms. Oh, here they are. I think. They are for me. But they may not be for you. I promise you, if you go online and Google search a Fibonacci sequence, some people start here at 0, then 1. But the rest generates.
What was the explicit formula again?
For this one, for the Fibonacci sequence, it's got a special name. And it's given in terms of phi, the golden ratio, which I did not give you. In this particular example, I did not give you an explicit formula. In Math 15, not only will I derive it out of thin air, but it'll become significant to us.
So the square root of 5 plus something over 2.
Yes, 1 plus root 5 over 2. It involves phi. Yes.
Which class is Math 15 again?
Discrete math. Have you heard about this discrete math here?
Do you actually teach that? Because I need to take that.
I taught it all the time.
Computers.
The last time I
Yeah.
taught it, there were so few students, and the budget prices hit so hard, the college demanded the math department slash a huge number of courses. The math department voted to cancel that one out because it didn't enroll full. So,
Took discrete structures last semester. But
now
I
discrete
take
structure,
that,
same
yeah.
course, but taught in the computer science department. It's
Yeah.
just that they emphasize the computer science part of it and emphasize the math part of it.
Okay.
To be honest with you, I cheated. The reason why I resurrected that class is I had too many Math 3 students complain to me that they're still here. There's no math classes to take. So I snuck in and changed the prerequisite, changed the number of hours I taught the course, and did it officially. And I just sneaked in some more advanced topics. Because 33 students just went more than
So you're going to be teaching that ever again here? Or?
I sure hope so. I will teach that. And the college has told me that I can teach that course now, next semester, as long as the math department agrees that we cancel another course, and I put that one in. And the few times I asked, the math department won't let me finish my sentence. They just yell at me, no. They're pretty strong on that. So you guys be honest with me, how many of you really work with the
Take that.
Fibonacci sequence before?
I've seen it before, I have worked with it.
Can I have 5 minutes of playtime before the break? Just 5 minutes. You guys, wouldn't this be so cool? If you and I can come up with a rectangle that has this really beautiful quality. That if I section off a square on the inside and come up with another rectangle that's similar to the original big one, I'll proclaim that's a golden rectangle. And I think the ratio of long side to short side of a golden rectangle is just a constant. It doesn't matter how big the golden rectangle is, the ratio of long side to short will be the same. So can I just make up a name for the long side? And imagine the short side is just equal to 1. Then if I could solve for x, I'd come up with the ratio of long side to short side of the golden rectangle, and I'd come up with the golden rectangle. Do you guys know why the Greeks looked into all this? Remember the Greeks?
They thought it was like holy or something.
Not quite that much. They thought it was just pretty. They thought it was just the most aesthetically pleasing rectangle to be on.
Doesn't it show up in like Nautiluses and Sun?
Oh yeah, I'll talk about that in a minute. Yeah, particularly Fibonacci sequence.
Like I read the book, The Golden Ratio.
Oh, did you really? It was a very good book. I read it.
They talked about they thought it was like the most aesthetically pleasing.
Yeah, so not really magical or anything like that. Again, they were the Greeks. And it was not the early Greeks. We're not talking Pythagoras. So we're not talking about a bunch of nothings. But if I could just find that ratio, that'd be so cool. So check this out. Remember, I'm sectioning off a square, and therefore what remains here on the inside is another rectangle similar to the big one. Meaning if I put it on a piece of paper, zoom out appropriately on a copy machine, I'll get the original one right back. It's just that for the smaller rectangle, what's the length of its largest side? What's the length of the smallest side? Because this is x, and that's 1 since this is a square. And I think if I were to proclaim that those two rectangles are similar, then I think the ratio of the length of the longest side of the large rectangle to the length of the longest side of the small rectangle should be the same as the ratio of the length of the short side of the large rectangle to the length of the short side of the small rectangle. And now if I multiply both sides by x minus 1, I get this. Oh shoot, that's quadratic. Oh no, it doesn't factor nicely. But the quadratic formula says that x is equal to 1 plus or minus the square root of b squared minus 4ac all over 2a. Oh no, it can't. Actually, I made a mistake. X and the length of the side of a geometric figure. And 1 minus root 5 is negative, so I better reject the negative equivalent square root. And I really do not know why this is the case. But if you guys measure these things carefully, credit cards are so darn close to golden rectangles. I have no idea if that was intentional. I really don't. And the golden rectangle, unbeknownst to the Greeks, pops up all over the place in nature, like nautilus shells or just things like broccoli and cauliflower and pine needles, not needles, pine thank you, cones.
Is that a fractal pattern?
Yes, this is actually the basics of fractal geometry.
When you say close, do you mean midpoint formula close or substance formula close?
Neither. I just meant there is an approximation. Last time I computed it. Here's something really cool. This is really slick. Maybe you know this number is approximately.
It's phi.
Yeah, we call it phi. We use that symbol for it, phi.
1.61.
Approximately. You guys check this out. Plant your feet right here. The ratio of this Fibonacci number to its predecessor is 1. That's below the Fibonacci. That's below the golden ratio. 2 divided by 1 is bigger than it. 3 divided by 2 is 1.5, smaller than it. 5 divided by 3 is 1.6 with a bar over it. That's bigger. 8 this is 1.6125, smaller. 13 over 8 is bigger. It oscillates back and forth, but it gets closer and closer and closer to it. And I think if you took any Fibonacci number, divided by its predecessor, and allow n to increase by bound, you get a fixed real number r, which is nothing more than golden ratio.
Is this a harmonic series?
No, quite the contrary. It's not harmonic at all. Can I prove it to you? Because I do this to my math students.
Oh, I was just gonna ask, does this fall from the bounds of the squeeze theorem? Like, could you?
Yeah, that was
Fibonacci
kind of
sequence?
what I was.
And it has nothing to do with it. What's really going on is I'm just oscillating back and forth about the golden ratio, but hugging it more and more closely in an asymptotic fashion as it increases.
It's like damped harmonic.
I see why you're saying that. I'm so sorry.
Harmonic is a linear though. It's 1 over n. So that would just.
All right. It's just that when I use the phrase damped harmonic for motion, is I typically think of that amplitude, which is not a constant, as changing exponentially. And I think this amplitude, in the sense, is changing, decreasing, but not necessarily according to an exponential function. You guys check this out. What was that recursive formula? A Fibonacci number is equal to the sum of its predecessors. You guys watch me divide both sides by f of n minus 1. If it's true that as n increase that bound, this approaches some fixed real number, call it r, let's find out what it is. I think that fraction is just r. I think this fraction is actually 1 over r. Let me clear fractions, bring everything to the left-hand side of the equal sign. Let me solve for r with my math skills. Oh, but shoot, I'm not going to have any negative values. I've just proven to you that the ratio of Fibonacci number to its predecessor approaches phi as n increases with that bound. So the golden rectangle and the Fibonacci sequence are intimately related. Not that the Greeks had any idea what the heck the Fibonacci sequence was. Nor did I suggest a Fibonacci knew a relationship. But jeepers, past several decades, we're seeing so many applications for both those topics popping up in nature.
How does f n minus 2 over f n minus 1 equal 1 over r?
Well, don't you agree that this number is further out than this one?
Yeah.
And so I just think that ratio invertedly is just 1 over r.
I don't get it.
How about this? Was this my assumption?
Yes.
But does not mean the same thing as this. But doesn't that mean when I invert these two, I get this? So now you,
You did something weird with this, with the subscripts.
oh, that is weird, yeah.
Are you saying with the arrows, are you saying it's equal to R?
No, I'm sorry, I'm suggesting this, I'm being lazy, not writing everything. I really meant that as n increase that bound, let's assume this ratio approaches some fixed real number, because it seems to be. And if that's true, let's find out what the number R is. I found out, shoot, look at that, it's just a golden ratio.